Hello. Thank you all for coming to our last tutorial session for today. My name is Luis Intaimo. I'm a professor at Texas A&M University, and I'm the Informs 2018 co-chair. And I'm honored today to introduce our speakers for the session on coalescing data and decisions by three authors. We appreciate their contribution. We have Dr. Suvrajeet Sen, we have Junyi Liu, and Yunxiao Deng. Yunxiao Deng is a PhD candidate working with Suvrajeet Sen at USC in Industrial and Systems Engineering. Her research interests are in stochastic optimization, particularly numerical methods for solving two-stage stochastic programs with applications in data-driven decisions. Junyi Liu is a PhD student, finishing up next year, I believe. Prior to joining Suvrajeet Sen, she graduated from the School of Gifted Young at the University of Science and Technology of China with a major in statistics. Her research interests include models, algorithms, and applications of stochastic programming. She is also devoted to building the bridge connecting the gap between data science and decision science with theoretical fundamentals and computational efficiency. She was actually a recipient of the graduate school graduate fellowship in 2015. Suvrajeet Sen is a professor in the department also, same department. Prior to joining USC, he was professor at Ohio State, and before that, he was at the University of Arizona, and that's where I happened to meet him. He has served as a program officer at National Science Foundation. He has done a lot of research devoted to many categories of optimization models, has published over 100 papers, with the vast majority devoted to models, algorithms, and applications of stochastic programming. His research portfolio has garnered over $10 million as PI for basic research grants in stochastic programming. He has served on several editorial boards, including operations research as area editor for optimization. He was also instrumental in founding the Informs Optimization Society and recently the new journal, Informs Journal on Optimization. He has made several plenary presentations at different conferences, and he also led a group of researchers who were awarded the Informs Computing Society Prize for the seminal work on stochastic mixed integer programming in 2015. He's a fellow of Informs, but more importantly, he is my academic father. So help me in welcoming him.
Thank you, Louis. If I knew that he was going to read through all of that, I would have given a much briefer statement. But thank you, Louis. It's always a pleasure to talk about things that I'm passionate about. And so these kinds of problems that we're studying today are extremely important for the ORMS community, because much of what we see today, let me just go over to the title of this thing. What we see today is a lot of work in machine learning applications, which are essentially more driven towards computer scientists, electrical engineers, problems of image processing, problems of things like voice recognition, those kinds of applications, which are not your standard ORMS applications. So this talk is actually motivated by more applications in ORMS, because we need to serve our field and make it grow in directions that are very new and very challenging. So hopefully you will get some new ideas from this talk, not necessarily completely new, but there will be a new fusion between optimization and learning, and that fusion will help our ORMS type problems. So I'm going to go over those kinds of issues here today. None of this is possible without the two co-authors here, that is my two PhD students, Yunxiao Deng and Junyi Lu. They have provided a lot of insights into what goes on in this paper, as well as other papers that are in the works. Also, we will leverage parts of our stochastic programming algorithms, and for that I want to thank Yifan Lu and Harsha Gangabanavar. And so what I want to do is to also acknowledge that much of this is going to be computationally intensive, okay? And we cannot be just proving theorems. We want to prove theorems because that's the basis for our field. But in addition to proving some theorems, we want to show that they are applicable to problems that are interesting to the community. And so many of the things that we will talk about have been implemented. And I want to show you that all of this can be done in a very systematic way, and that systematic way is going to be shown through this computational operations research exchange. And this exchange is intended for all of us. Everyone here should be able to get into this kind of a system and share their computational results and data sets, code, etc., so that the community can grow with it. Okay, that's our overall goal. So this last part is going to be in the last 20 minutes or so. And then the first part of this presentation will involve more the foundational algorithms. Okay, so here are my partners in crime. Yunxiao Deng on the left first, then Junyi Lu. Carl Kesselman, some of you from the 90s might know of him for distributed computing and Globus Toolkit. He is behind our core system. And then there are my former PhD students, Yifan Lu, who spent a lot of time cleaning up some of our codes and devising a really interesting concept, which I will share during the course of this presentation. Harsha has got some newer versions of stochastic programming algorithms, and he's been instrumental in a lot of challenging applications in power systems. And then finally, Jiajun Xu, who has been working on this core system. So let's get started here. The plan is I want to start at the very beginning. First, I'm going to start with some philosophy about uncertainty, and then go into the need for our ORMS community to move into the modern computing world and modern data sets, and that's what I'm going to talk about for a minute. And then we'll go into the more central themes of the tutorial, which is decisions with stochastic programming, statistical learning, and the connections with stochastic programming. The main theme towards the end will be learning-enabled optimization, and then finally computations and the demo. So the last two items will be delivered by Yunxiao Deng, and In the end, what we would like is for those of you who are interested to sign up. We will send around a pad of paper. We don't want to send spam emails. So I want you to sign up if you're interested in being part of the core system, and we'll set you up with it. Okay, so let's get started. Just the philosophy of uncertainty. One of the things that I find for myself is when I started studying optimization, it was a completely deterministic world, and we rarely ever questioned why would we solve a deterministic optimization problem. It was given that that's something that everyone is interested in, and we would solve it. And so what happens is that kind of a problem goes through what we would call epistemic uncertainty, which means that there is a lack of knowledge. When someone poses for you a deterministic optimization problem, before you actually solve it, you don't know the answer to the solution. So everybody is unaware of what the optimum solution would be. And then once you solve the optimization problem, that uncertainty that you had about it dissipates, and you have no more uncertainties. The uncertainty is all resolved at the end of solving a deterministic optimization problem. And unfortunately, that is exactly the same philosophy that we carry into the stochastic optimization world, treating it as though it is in the same form as epistemic uncertainty. That is, once we solve the stochastic programming problem, there is nothing more uncertain left. And the fact is, nothing could be further from the truth in most real-life problems. Because just because you solved that stochastic programming problem, you really have not provided much support to the decision maker about whether they should be following your model or alternative models. How do all those models compare? None of that is part of our repertoire. And this is what I would like to change, if nothing else, from this talk. Okay. So what I want to do is to emphasize that what stochastic optimization does is only mitigate the decision uncertainty. We only mitigate it, but we still need to provide more support so that you can actually figure out whether the decisions you're making are tenable to your setting. Okay, and this is something that what we will do is provide some tests beyond just saying, here you have your optimal solution. We're done. Okay, modern data sets. I want to talk to you about, many of you, I'm sure, those younger than me in particular, know about these websites, Kaggle, etc., know about how to go about finding data for your projects, okay? Unfortunately, people my age have not really caught up to running with data in that form, large-scale data sets. For instance, I want to mention to you a certain problem that is mentioned in our tutorial, which is this diet problem in the new millennium. Many of you have studied the diet problem. The diet problem is still one of the most well-cited examples of linear programming, and it was first set up by George Stiglitz in 1939. And the data set that went into that was essentially some manuals from the library, right? So they went and found the nutrition content and so on and so forth from the library. How many of you go into the library these days to find data? Almost no one, right? And so the data, though, is now very different as well. It's no longer just that you have some prices from 10 years ago. It's more or less that every retail outlet has their own prices listed up there. You know how much your meals are going to cost. You know how much their nutrition content is, way more than you will ever use even. Okay? And so the point is that the new diet problem should be such that we are able to use all that information that is at our fingertips. And that class of problems begins to look very different from the standard diet problem that we've had in the past. What I mean by that is the diet problem in the tutorial talks about how you might choose your sequence of meals during the week in such a way that your nutrition requirements are met, but you're going to choose meals, you're going to choose recipes, and choosing recipes ends up being a binary optimization problem. It is no longer a linear program. Okay? So what I'm trying to get at is, and when you choose things like recipes, issues such as, oh, I don't care for this is too repetitious, those kinds of things don't really happen because you can put logical conditions in your formulation that avoids certain kinds of choices. So in other words, the problems are no longer your standard linear program. They become integer programming problems. They become much more realistic. And one other important aspect of this new kind of formulation is the notion of using data from the websites. For instance, you can go into these websites and find recipes that have likes and dislikes and comments, and you can use those likes and dislikes and comments to create objective functions that will give you an attractive set of recipes to choose from. Okay? So in other words, this combination of using data together with decision models gets a much richer class of models than you've considered till today. Okay, I'm going to go on now, basically pointing to the fact that analytics problems of today needs not only a strong foundation in analytics, but also there's a lot of data, and that data can provide new classes of problems, etc. All right, let's go on with the more fundamental questions of this presentation. And that is, I'm going to start with a simple stochastic programming model. And this is one where you are, choosing decision X, which is supposed to be feasible, and that feasibility is shown by this X in capital X. And then there are two terms here. The first term is deterministic, and the second term depends upon a random variable, omega tilde. And this, what we are going to use here is a two-stage stochastic program. This H, when this H has a definition that is also a value function of an optimization problem, then this is called a two-stage problem because the first stage has this cost and the second stage is the value function of a random problem. And this kind of a problem is your standard stochastic programming problem in two stages. But if you had this H defined in a recursive manner, in a nested recursive manner, you could have a multi-stage problem as well with this setting. Unfortunately, these problems can become arbitrarily complicated. So I'm just going to stick with the simpler two-stage version and show you how this two-stage version will also be useful in the learning setting. Okay, one of the things that in these models is we assume the distribution of the random variable omega tilde is given. And when I say it's given, and people will often say, oh, we really don't have random variables, we have data. And of course, this is an abstract setup. In this abstract setup, we can include things like empirical distributions, just the data that you observed. That's possible. In any event, we're going to not quibble about random variables or not, and because later on you will see that we will create random variables of different kinds and examine problems of different kinds. So we'll go on with that. So one of the ways that people think about the stochastic programming problem is by using the sample average approximation of that problem. By the way, this sample average approximation is not an algorithm. I just want to be sure that people understand that this is simply a finite dimensional approximation of the original problem. The original problem may not be finite dimensional. This is finite dimensional. It doesn't tell you how to solve anything, okay? And unfortunately, a lot of people think that this is an algorithm, because you still need an algorithm to do the numerics to solve this problem. And exactly how you try to solve this problem will determine how successful you are, okay? But anyway, this kind of problem in the learning literature has been named empirical risk minimization. And the word risk does not mean the same thing in the learning world as it means in the ORMS world. I won't go into risk modeling, etc. But clearly, this is not risk in the ORMS sense. All right, I'm going to give an example here. This is an example for network planning. It's a very simple example, and what I want to do is to suggest that, let me see, I missed something. Okay, so this problem is one where what you're trying to do, it's a linear programming type problem where you've got 3 links that you need to size, and these 3 links, some of them can fail. So if this link fails, then the whole connection there is removed. If that link fails, again, the whole connection is removed. But this link from A to C, that A to C link is such that it cannot fail. You pay a lot of money for it, and it cannot fail. Okay? So in this particular example, I'm going to say we have $10 to spend, and spend it the best you can to minimize the number of lost calls, expected number of lost calls. Okay, that's a problem like this. And when we use linear programming to solve such a problem, what we would do is to replace the randomness by the expected values. Okay, what happens there is the following: that we will get solutions that look like this. That this A to C is a very expensive link, and therefore will not be included. We have $10 to spend, let's say. What happens in this particular data set is that we spend $5 on this one, we spend $5 on that one. $10 gets spent, and here's the network. This network, many of you will recognize, is a tree. And why is it a tree? Well, linear programming gives you basic solutions which end up being trees. Okay, so you get a tree. Now, what happens when you put this in practice? When you put this in practice, someone comes and blows up one link, then at least one node will be without connection to the network. Okay, and what does that mean? That means that your crew is running around trying to fix this problem. So yes, it is true that you've solved this optimization problem, but you didn't consider failures. And now the crew is going around fixing this problem on a daily basis. Well, not daily basis, but whenever it fails. Okay? And so you've added more work to the crew by solving it in this form. On the other hand, let's figure that we solve a stochastic programming problem. This results in a fully connected network, and the amount of money in this particular solution is we spend $4 on this link, 3 here, 3 there. Okay? And now when it fails, as long as 2 links don't fail at the same time, you're always connected. Okay? So your operations problem becomes a lot easier to manage than the problem that we had when we solved the LP. Okay? This is what I mean by saying that by solving an optimization problem, we have not resolved the aleatoric uncertainty. Okay? All right. Let's go to a more advanced problem. This is a case we did many years ago. This instance is a similar problem, but now it's a much larger instance. It has 89 links, 706 routes, 86 demand pairs. And if you look at all the possible ways in which these things can go wrong, there are 10 to the 70 scenarios. Okay, that is an astronomical number. Okay, Carl Sagan would be proud of me for this number. And what we did then was we solved a problem like this using the codes of that time, early 1990s. They did just fine because we tried to be as clever as we could with the computing that we did have, and we got some results. But let me show you what model validation for SP means. Okay, I've taken this from a paper by Jeff Linderoth, Alex Shapiro, and others, and Steve Wright, others being Steve Wright. Okay, so this paper shows you how model validation has a lot of uncertainty itself, because you go in there first because you didn't know what the sample size ought to be. You started out with sample size of 50, and then you solved this problem, whatever that solve meant. Okay, so you approximately solved that problem. And then you calculated some lower bound, and you calculated some upper bound. Okay, and I will slowly clarify why this lower bound is in quotes. Okay, this lower bound is in quotes. Keep that in mind. Then we'll go to a sample size of 100 and solve the problem again and do this. You know, we create another lower bound, another upper bound, and so on. Now, let's go on to 500 here, say. And now you have, again, a lower bound and an upper bound, and here's a pessimistic gap. The word pessimistic gap is being used to denote the upper side of the upper bound confidence interval minus the lower side of the lower bound confidence interval. Okay, so that's the worst case thing that can happen to the sample mean estimate. Okay, and now let's take a look at this line. If you take a look at this line, you will see why this lower bound is in quotes. Because if you take a look at the first number, 10.1 was a lower bound. Well, this seems to be higher than this upper bound. Okay? And so just solving this problem at 50, where a lot of people might stop, will be misleading, right? Because what you're seeing is a small sample, and in that small sample, when you calculate a lower bound, this has tremendous bias. Okay? You've increased the size, but the pessimist, now if you come to SAA 100, you've increased the size, but the gap didn't decrease that much. Okay, it's now 2 out of 10, which is a 20%. So for optimizers, 20%, that's a little much in terms of a gap. So we figured that we're not ready to stop yet. Now we do SAA 500, and that has reduced it to some respectable number, let's say 0.445, that's about 4%. That's a little bit better. But still, we may not be satisfied, and so we say, okay, let's increase this to 1,000. And now take a look at the sample size again. It's 1,000. You've doubled it, but the pessimistic gap has gone up. In other words, what I'm trying to caution you is that when you solve stochastic programming problems, sampling or otherwise, you're doing approximation. And when you're doing approximations, okay, just to solve it once and be done is misleading. Right? You have to somehow replicate until you figure out that you're getting some stable answers. Okay, so the validation involves a lot more work. And finally, anyway, so since this increased, well, we are not really stable yet. So finally, we raise it to a 5,000. And with 5,000, now it starts getting to look like more stable here, okay? But I want to now mention that these things should always be replicated. When you're sampling, you should replicate it because your solutions are going to be one outcome in a sample path. And so, you can't rely on them as being great solutions. Excuse me. I steal this, whoever it is, I don't know. I'll leave the other glass for Yunxiao. Okay, so let's continue here. The point of this is that model validation for stochastic programming, okay, cannot happen by solving one instance, okay? In this particular case, they say that they replicated the runs 7 to 10 times for each sample. And so 7 to 10 times would mean about anywhere between 35 and 50 instances. So there were 35 to 50 instances solved. And not only that they were solved, they had to compute upper bounds. And how would you compute upper bounds? You would fix the decision. And fixing the decision, you would do some sampling. And you would solve many more problems, right? So there's a lot of work that has gone into this table, okay? And so the reason that we are actually trying to create this website with our core project is to ease the efforts for model validation of this kind, because that way you're able to write out the workflow that is necessary to do the validation and then have the computer do this work for you rather than you manually trying to do this. Okay, so we're trying to encourage these best practices, hopefully. Okay, so now for those of you that don't want to use validation, I'll show you another kind of validation, which I call verification. It is not really validation of in the sense of validating your optimality, but it's more of a verification that perhaps what you have is a reasonable approximation. So here is a study that we did along with that SSN study in the 90s, 94, I believe. Oh, 94 was the year the paper was published, 91. So it's a very old paper. And it's amazing that the word hasn't gotten out. So thank you for coming here. Please get the word out. That verification and validation are very, very important parts of stochastic programming. It is not just solving one SAA instance. Okay, back to this exercise here. So the first thing here is this first figure, I don't know how clearly you can see this figure. I can see it very clearly, but perhaps you not so much. But what it is basically it's a set of points starting here at about 25, goes up, and then comes down here. And what this is one run of a stochastic programming algorithm that we call stochastic decomposition. It's one run. And in this one run, we basically did the following. We took we took about 11 points along the way. And as the iterations made progress, we recorded some solutions. We recorded the solution at decision at iteration number 1, iteration number 100, 300, and so on and so forth. Okay? Then we took those decisions and put them into an evaluation scheme. Run the samples for each of those decisions and calculate what happened to the optimization algorithm. What did it do? And then we compute these quantities, finding upper bounds at each of these solutions. Okay? That's one graph. Having done that one graph, now we created a simulation model, a discrete event simulation model, because a lot of the analysts were using discrete event simulation to do their planning. And so we took their model and put the same solutions into their model to find out how much the objective function would be. But they didn't evaluate our objective function. The stochastic programming objective function was minimize expected number of lost calls. The discrete event simulation objective function was blocking probability. How many calls were blocked? Okay. So when you look at that, then you say, how am I going to compare these apples and oranges? But we anyway go ahead and do the simulations. So we do the simulation and see what happens. The blocking probability goes up, and then it goes down, and so on and so forth. But you see, it's the same kind of flow that you're observing in terms of each objective. Okay? So in other words, at least for that set of runs, you were able to validate your thinking in terms of two alternative models that didn't have anything to do with each other. Okay? And that should give you a sense that the final solutions look pretty reasonable, because both of them come to around the same kind of solution. Now, the difficulty with this one is that it doesn't really do validation of optimality. All it is doing is keeping track of whether the two models have any evidence of not agreeing with each other. Okay, so what this says is that the two models, they seem to not disagree. Okay? When you don't have enough computing resources, this is what you do, and that's why 1991, this is what we were doing. Okay. Anyway, these kinds of problems will happen today as well. Even though we have a lot more computing power, we still may not be able to do the number of replications necessary. Okay. All right. So now I want to go over, just to make the transition into more modern problems like support vector machines. Everyone here has heard of support vector machines, so I don't need to really go over this picture. But essentially, what we're trying to do is to find this separating hyperplane, distinguishing these two sets. So I'm going to skip through that and show you that the model for this is written in the following form: standard SVM model, where this delta here tells you the distance of the point from the separating hyperplane. Okay? And these betas are the coefficients of the separating hyperplane. Okay? And the problem is essentially a stochastic programming problem. If you look at it as a model, this is similar to a stochastic programming model. But traditionally, this SVM problem was solved as a quadratic programming problem. Quadratic programming problems, which would mean that you solve it as one all-in-one formulation. What I mean by all-in-one formulation is everything is put in one quadratic program. And you hit Cplex, Gurobi, whomever, to solve this large quadratic programming problem, and you get your answers beta. Okay? Betas give you the separating hyperplane. All right. Now, what is the advantage of looking at it from a stochastic programming point of view? First, let's see what makes it a stochastic program. Those betas, we could just as well call them x's, and so you have that C of x function, which is a quadratic. And these functions, these h's from stochastic programming, are essentially these max functions. So those deltas that were there in the previous slide are essentially these h's, which are max functions. And so this is essentially your stochastic programming formulation. And you can solve this using stochastic programming. What is the advantage of that? If this n is very large, say you're doing big data problems, then you don't have to store all of them in the all-in-one formulation. You could solve it using some decomposition type schemes. Okay, so that's the advantage of using stochastic programming here. People already know how to do this in the machine learning world now. There are new algorithms here, subgradient methods, stochastic quasi-gradient methods, and so on and so forth. So you can solve these problems using stochastic programming. And the advantage of this is that you really don't need to store all your data in the optimization part. The optimization part can do some sampling, subsampling, you name it, all kinds of schemes are available, okay? But ultimately, when you use these subgradient methods and similar schemes, at the end of it, you do not have any solution guarantee. You have asymptotic results. So if you take a look at machine learning literature, you take a look at NIPS, etc., you will have a lot of asymptotic results. But when you run the algorithm, you really don't know what part of the asymptote you're at. Did you even arrive there? We don't know that. Okay. However, in stochastic programming, we have tried to maintain our fondness for optimality tests, and we have ways to guarantee how close you are to optimality. Okay. So that's one of the advantages of doing stochastic programming in these kinds of applications. Okay, now let's move over to, so my review of stochastic programming is done. Now I'm going to go into statistical learning and then see what the connection is between statistical learning and stochastic programming. They may seem very different, but they're really not. So let's start with the first difference. And the first difference is that a lot of statistical learning literature, they start with covariates. Covariates being these Z's and W's are both random variables, but Z denotes a predictor, W denotes a response. So for instance, when you have data, they might look at, they will look at someone like me and say, can this be a football player? They'll take my weight, they'll take my height, they'll take my muscle tone, etc. And then they'll try to predict whether or not I'm a football player. I see some people shaking their heads. I don't think I could even qualify. I have played some of the kickers in tennis. This is not the same thing. Okay, I'm sorry. Let's just go on. Okay, so the standard assumptions in statistical learning are, you assume that these ZI, WIs are IID, observations of this pair of random variables. And what you do is you divide up the data set into two pieces. Let's call them T and V. And T would be the training set, V the validation set. And the point of doing this is to see if you can do some cross-validation by setting aside this set of data points in the validation set. And the goal is to discover a relationship between Z and W. Okay? And so, when you do linear regression, you get something like this. Your model has the inputs Z, and you do a prediction as beta 0 plus this beta j zij, and then there could be an error, and the error term is showing up here. But you could also do other kinds of models, and you could do nonlinear regression, in which case these zj's get replaced by phi of zj's. And then you could have things like vector errors as well. So not just the constant should have an error. You could have an error with the coefficients as well. Bayesians would love me for this. But anyway, I'll just put it up there. So there are alternative models that are possible. We can posit alternative models. And now we should ask, which of these models would be most reasonable? Okay? And again, there are more details. There are alternative models that might come about depending on how you choose the errors. Some of these errors you may assume are correlated. You may assume non-correlated. Again, these are all alternative models. Okay? And you can have many more of these. And then in the end, you want to figure out which of these models best describes your data. So the focus is description of that relationship and the data that you use to discover that relationship, right? So that's what the statistical learning folks are up to. So if you look at their solving protocol, it looks something like this. Divide up the data set into training and validation. And then you have these two processes. First, you do your your regression calculations, and then you do your validation calculations, and then this series of things can go on. These diamonds here are actually hypothesis tests. So you check to see whether you have enough generalizability, and so on. So this is what I would call the statistical learning protocol. And what I want to see is whether there are connections between statistical learning and stochastic programming. Okay? Let me take a quick show of hands. How many think there is absolutely no connection between statistical learning and stochastic programming? Anyone? No one. Everybody believes that they're very, very closely related, right? Then you're on my side. Okay, let's see. So there's one difference. The root is optimization here. The root is statistics there. So that's sort of just obvious. But let's take a look. And I'm going to show you some distinctions between the two, though. And so let's go ahead and see. So for the first thing is that SP does the decision optimization, whereas statistical learning has this parameter optimization. And there is a difference between these two because in decision optimization, we often run into inequality constraints. And inequality constraints, being one-sided, create objective functions that happen to be often non-smooth because of the one-sidedness. Okay? On the other hand, in the parameter optimization world, we typically deal with either unconstrained parameters or sometimes equality constrained problems. So for instance, when you're doing, when you're trying to fit for a dynamic system, the dynamic system might have its dynamics, and that dynamics is typically an equation, a dynamic equation. So you would have parameter fitting happening in that setting. So you could have slight differences like this. So it's not uncommon for the statistical learning world to assume differentiability. It is not common for stochastic programming to assume differentiability, just because of the value function non-differentiability. Okay, these two items, sample average approximation and empirical risk minimization, those are essentially the same things, not any different at all. And then we have, let's see, in terms of the theory, they both tend to rely on some mathematical notion of uniform convergence. Okay, and so mathematically speaking, they're deriving their results from similar ideas. And then algorithms, slight differences. Notice one thing, that on this side, you won't find something like the L-shaped method. And the reason for that is constraints are not such a big deal over on this side. Constraints are a big deal here. So things like feasibility cuts are necessary in the Bender's type algorithms because you're looking for constraints. On the other side, you don't really worry about the constraints so much. There is one other important thing here that they do and we don't do. We do confidence intervals. And remember, confidence intervals are intervals that are for the mean, right? You're calculating how confident you are about the sample mean there. The one thing that they do that we don't do is this notion of prediction intervals. And the word prediction intervals really means it's a population statistic, which means you're looking at what could happen once you adopt this model. The range of things that could happen. So if it's a 95% prediction intervals, then there is a 95% chance that one of those events could happen. Okay? And so that is something that in stochastic programming we need to be able to support, because once the decision is made, remember, we have not resolved the uncertainty. Anything could happen. And that prediction interval tells us what is the 95% chance of something happening in that region. Okay, and we should be prepared for that. Okay, validation, we have some validation, and the reason I say limited validation emphasis for stochastic programming is because while there are many people that are using good validation techniques, there are a lot more who are solving small sample stochastic programs because they looked at the book on linear programming and found this chapter which solved this block angular problem. They solved that block angular problem, and as long as they have more than one scenario, they call it stochastic programming. Okay, let's not do that anymore.
For instance, for mean variance models in financial optimization, the Markowitz model, we have an optimization model for stock returns, and
Can we go over this later
because
at the end? And at the end, just make a note of this, okay? Because I think I'm running a little bit behind. So if we will continue this conversation after we're done, okay? All right, let's continue this, and then I would posit that stochastic. I would posit that the statistical learning algorithms are essentially optimization algorithms. So it's optimization-enabled learning. And this one, on the other side, you know, we will hopefully get to some learning-enabled optimization soon. All right, let's talk about a problem that I call the Wyndor production planning problem, borrowed from the famous book, and I'm honored to have Fred Hillier here. So the book has this particular problem, which is on producing two doors, door type A and door type B. Two doors, and you're trying to maximize profit by using capacity well. And the capacity shows up here in the right-hand side, which has 8 amount of resources in the first constraint, 24 in the second constraint. So these are 3 plants where these doors are made. And then you maximize this. This is the first problem in the Hillier and Lieberman textbook. And it has been very good for teaching linear programming because people understand that these are inequality constraint problems. But one of the things that the authors note right at the start is that there is ample product demand. And ample product demand means you don't need to worry about how much you can sell, okay? And so you solve this linear program, you get your answer, and you go on your way, you're ready for the world, okay? Now the world, however, has different ideas because they have seen some sales data. And the sales data, now this I'm making up here. This is some data that I picked out of this book. I'm basically taking an OR book, I'm taking a statistical learning book, and creating a problem together now, okay? And in this book, they're saying that sales, the joint sales, are dependent on how much advertising you do. There's advertising on TV, there's advertising on radio, and depending on the amount of advertising, there'll be a certain amount of sales. Not there will be for sure, but that's what they've observed. So you can think of this as being the sales here as being the W, the response that I wrote earlier. And the Z's are these spots on the TV advertising and radio advertising. So the Z's are these 2-dimensional, and the W is 1-dimensional. Okay? So now what the question becomes is that how much TV and radio ads should I put on for maximizing my profit? Okay? Now the CEO comes in and tells the analysts, please take a look at this sales data and tell me how I should modify this model. Okay? The analyst looks up and says, well, those are random variables. We don't optimize random variables. And the CEO says, heck, I'm the one deciding. How is it random? He's the one deciding how much TV ads to put, how much radio ads to put. Why is that a random thing? So randomness is often the issue of what you know. If you don't know how the CEO makes the decision, that to you is random. So the analyst finds it as being random. But it's not really random. Okay? So the question now becomes, how do I set up and solve a problem like this where the sales could actually impact my profitability? Okay? So, so here is my suggestion. My suggestion is to first think of understanding the relationship between the covariates. So in this particular book from James and company, they created this model as a model of the relationship between Z and W. A very common thing to do is now to think of, oh, that's my linear regression, so I have a linear constraint. I can just add my linear constraint to the other linear program, and then that's it. I'm ready to go. Okay, let's see what will happen. We'll try that. Okay, that would be another model, right? So we want to give everybody a chance to play in this system. So think of it as a horse race. When someone takes their horse and says, I want to have this horse be in the race, you don't say no. Fine, let it be in the race. Let's see how it does. Okay, so we'll also put this one in the race, and let's see what happens. All right. So anyway, the problem, I've now set it up as a marketing production coordination problem, which also looks like a stochastic program. If you take a look at this, here's the cost of the TV advertising and radio advertising up here. And then this is the profit, and the profit is coming from here. Okay, so this would be an appropriate model if I knew the distribution of W given Z. But I have data. I don't have the distribution of W given Z. Okay, but let's say I decided, that's too much work to get the distribution. I'll just do sample averaging. Okay, so let's try this. I'm going to use sample averaging, and let's see what I can get. So one way to do it is to say that, I think I might have missed something. I want to say something here that I missed. That this sample averaging, though, is not wise. Why? Because this doesn't have the distribution of sample averaging. Right? I mean, the distribution we don't have. This W given Z we don't have. So it's hard to do sample averaging this way. So what one can do is to say that I will use some sort of a penalty between Z and X. Remember, in optimization, we are very fond of penalties. In fact, you will find a lot of papers, especially simple recourse optimization papers, where they will say, I'll put a penalty, Q plus and Q minus, the deviation from the random constraint. Okay? That's fine to set up a stochastic program like that. You'll find it very difficult to actually validate it. I'll show you why. So in this, I can create a problem like this, that my penalty says I should not be using Z's that are not equal to X. Okay? And if I do that, I have a two-stage problem that looks like this. Now, I have a penalty term here, and I have a W here. So please take this problem in. We have optimizing again with the W and Z together up there, which would be like the omega tilde that I had in the SP slides. And then this ZI is a penalty term in the objective, and the W is the sales. So I say the total sales has to be less than or equal to WI. So this is a completely data-driven setup. There's no need for distribution here. Right? Okay, so let me solve this problem for different values of the penalty M. Okay, and here's what happens. So when I use different values of penalties, you see what happens is that the objective function that we get from the model with penalty is all, can be negative because you've got large M's sitting there. Okay, so you can have negative values, but even if you don't account for the negative values in evaluating the objective, you will still get objective function values that are not close to the validated objective functions. Okay? Now, you may have solved a stochastic program, in quotes, solved my stochastic program because you solved that block diagonal structured problem. But you really haven't really got a solution that you can support because your objective function on either side, what it's predicting, is nowhere close to what is being validated. Is this making sense? So, first thing we have to recognize is that stochastic programming directly cannot be used for this problem. Okay, you cannot use this stochastic programming for this problem directly. But we have a strategy. We'll do something, and let me show you what we will do. Our strategy is, how much time do I have? Louis, how much time do I have? 30 minutes, excellent. Good. So, let's see what we can do. So our strategy is that we're going to use this model. With this model, we're going to try to figure out how to understand the relationship between W and Z. We will do some inference on this relationship and use that within the decision model. So what it'll look like is this. We'll first do some statistical learning. Then we'll stick it in that statistically learned model will come into the optimization model. And then we'll do a validation. So this can go in the cycle. Now there are multiple ways of doing this. One is if I do statistical learning and learning-enabled optimization together in this loop. If I continue in this loop, we call this coupled learning-enabled optimization because you're iterating with the optimization and statistical learning at the same time. Okay? However, if you don't want to do that, the simpler thing to do is to say, let me solve this whole thing, and then we'll do this optimization, and then we'll do the other. I'll talk about situations where either one is appropriate. And so let me describe what happens. So these alternative formulations, what we call are models with disjoint spaces. So if you take a look at this model here, it's again got W given Z, but Z equals something from its space, which is not the same as X. But here, you can have Z equals to X and X here are the same. This latter problem is what they call decision-dependent uncertainty and creates typically non-convex problems. These ones, on the other hand, create convex problems. The top ones create convex problems, the bottom ones don't. Okay? And so the bottom ones may not. We can create ways to approximate. Okay? All right. So so the basic sequential Leo is what I'll talk about today. And many of the applications for this kind of a problem is where a current example would be things like you have a hurricane path. You're predicting a hurricane path, and based on that prediction, you're going to choose your evacuation plan. That hurricane path is not going to be affected by your decision making. It's going to do its own thing, right? So in that case, you would go in this form where the two, optimization and learning, are not going hand in hand. Okay, learning happens first, optimization happens later. Okay, in other kinds of problems, you can have in this decision-dependent randomness, you can have the models work with together. So we have some examples on having pricing and demand going together. So those kinds of problems will have this approach that we call CLEO, coupled learning-enabled optimization. One of the most beautiful things about this term Leo is that I can cook up all these nifty names. There is one here, Leo with non-parametric models called Leon. But the point I'm trying to make here is that there is a variety. There's a whole variety of combinations. Once you say that I'm going to allow both fields to play together, there is a variety of applications and variety of methods to put together. Okay? So with that, let me go over to what the complications are. What happens is that these are composite stochastic optimization problems. What do I mean by composite? Well, you've got the composition of the statistical learning side and the optimization side. That composition creates actually a doubly infinite problem, because each one is actually officially an infinite dimensional problem. You don't know what the outcomes are. So each one is an infinite dimensional problem. Together, they're doubly infinite, and this is what I mean by doubly infinite here. That is, you have data and decisions. And this is my picture of infinity. You can keep going. You can't ever come to the exact solution because there is no finite time solution for that. And so, what are we going to do? We're going to try to manage this infinite dimensionality, which occurs in both dimensions. And so now I'm going to introduce another thought in your mind, which is the curse of infinite dimensionality, not the curse of dimensionality. Okay, so let's see what we mean by infinite dimensionality and how we combat it. Okay. So again, let's go ahead and see how we capture these covariates. And one simplifying thing we can do is to make what is called this homoscedasticity assumption. And this homoscedasticity assumption is that the error distribution is homoscedastic. That is, it does not change with the variables. Okay? So here, you immediately have gone from infinitely many distributions to perhaps one class of distributions. Okay? This is a simplification, and then what we do is whenever we do these simplifications, we say, well, we'll try to validate it. If it does not validate, then we will not accept the model. Okay? So that's one thing that we will do. Well, what we gain is creating much simpler distributions, and these distributions you can get directly from doing your regressions. For instance, if you have an additive scalar model, this could be your normal random variable. If you have more general errors, then this is a multidimensional random variable. Of course, these are causing the problems to become harder. Okay? These are because now you've got multiple dimensions. And so, for instance, if you look at this model here, where you have the error terms showing up for all the coefficients, there are as many coefficients, there could be as many coefficients as there are decision variables. So if you have a decision problem that has at least 100 decision variables, then you've got a 100-dimensional normal random variable. That's really large. Okay. All right. So the other thing that I want to mention is that when you have these kinds of infinite dimensional problems, it is easiest to reduce variance by doing replication. Every simulator here recognizes the value of replications, right? That's how we get confidence intervals, etc., by doing these variance, these replications. And so for stochastic programming, because these are going to end up looking like stochastic programming problems, I want to mention this concept of a compromise decision. This notion of a compromise decision is similar to what statisticians call bagging. And basically what we do in this is that we replicate the solves. So think of you solving a stochastic programming problem using benders. At the end of each bender's solve, you have a value function approximation, correct? Take all of those value function approximations, don't throw them away. Now bootstrap those value function approximations and create a new approximation. And that bootstrapped approximation gives you a decision, because you can now solve that bootstrapped approximation. And that bootstrapped approximation is what we will call a compromise decision. Is that making sense? It's sort of similar to this statistical idea, but it is in the objective function space rather than in the decision space. Okay, and you will see enormous changes in your variance estimates from the solutions. Okay, so how do we do that? We solve this compromise decision problem, and wherever there are these approximations of infinite dimensions, I start putting this. Okay, that these are, you're trying to get a handle on the errors from your finite dimensional approximations. This is sort of critical in what we're trying to do. Finite dimensional approximations, and hence there are errors. We want to get a handle on those errors. And by doing this, we reduce the variance of the decisions. Because remember, when you do replication in simulation, there is one advantage. You're not changing your decision, you're just simply evaluating a decision. Okay? When you replicate stochastic programming, on the other hand, you're getting different decisions with every replication. What should you do? What you should do is this, because this actually will reduce variance for you. Okay? So when you replicate, you need to somehow close the loop by giving one recommendation for a decision. You can't give many recommendations. Okay, so those are things we do, and what basically you want to look at is this, that the actual objective function value of the compromise decision is less than or equal to this quantity. And so if your n, which is your sample size for each batch, and if your m is the number of batches, this is the rate at which the error shows up in f bar, which is the grand mean objective. This grand mean objective is computable. This part we don't know, but if this nm is very large, because you've replicated, that nm can be very large. And if this nm is very large, the error is small, and the objective function value is less than or equal to what you see there. Okay? Which means you now have a bound on the decision x. Okay, so this is the other thing that I want to mention about approximations. Functionality in every which way. We're not seeking deterministic optimality, A. B, will give you something to shoot for, so that if you run an algorithm and I run an algorithm, we have a way to compare. That if I say that I'm going to give you a certain level of reliability, and you can give me the same level of reliability with less time, you win. Okay? Without that, there's no comparison. Right? So when you do this machine learning, the reason it is so compelling is that when they end up with pictures. They'll give you, see, I got this noisy picture to now look like something that I can recognize, and therefore I'm good. But that doesn't work for decision making in the corporate world. There is no picture of the future. Okay? So we need to be able to give some measure that people can all compare and come to a conclusion, well, this algorithm did better than the other. Okay, so I'm going to skip this part here. This gets too technical. I'm going to skip it. But it is there in the paper, so if you want to, you can read that paper. And if you don't like what you read in that paper, there's another paper, you can read that paper. All right, let's go on to model assessment, because I now have maybe not that much time. I have maybe a minute. So I'm going to go over this model assessment and turn it over to Yunxiao. Model assessment essentially is a way to figure out from the decision that you've made with all the approximations that you've put up, now you want to figure out among all these models, which is the best. It's not telling you optimality. All it is telling you is among all these models, which one is the best. That's what we want to find out. Okay? And so there are certain terms that may be new to you. There is something called generalization error, which we've defined for optimization. This is a term we borrowed from statistical learning, and the actual formula looks pretty similar, but the arguments behind this formula are slightly different. And similarly, we will show you some ways to compare models and choose which one may be more attractive than the other. Okay, Yunxiao, why don't you come on over and okay, we have 15 minutes for all of this.
All right, it's my turn, finally. So I'm gonna go over the last part, which are the computations and a short demo of our core platform. So let's see. So we will go over this Leo Wyndor example. So this is the workflow figure for this example. And as what Dr. Sun has presented, we have the input data from the Introduction to Statistical Learning book. And we put a multiple linear regression model. And in this example, we chose 3 different alternative error models. And the first is the deterministic forecast model, and then normally distributed correlated model, and finally empirical additive error model. And for those 3 different models, we're going to solve them using either deterministic LP or stochastic optimization solvers. And then we will do several validation methods within model, and then finally we'll compare all those 3 different solutions, do the validation across models, and then give our recommendations. And so this is the input data. We have shown this. And then this is the predictive model we have. And we have 3 coefficients. This beta hat is the mean value, and we have the error term. And this is the basic model we have. And for the different alternative models, we have different choices of this MQ here. It's the, which, so for this first one, the DF, we just use the fixed value, the mean value of these 3 values. So in this case, this whole problem is the deterministic LP model. And then for the normally distributed correlated model, here we have three random variables. And those 3 random variables are normally distributed correlated. And finally, this is the more of a data-driven model. So we just observe the distance of the predicted value and the true value in the training set, and we take this epsilon 0 here. So in this case, we have 1 random variable. And in the validation within model, we have different metrics here. So we have validated objective confidence interval and prediction intervals. And we also take the t-test, f-test, and chi-square test to measure not just the mean value, but also the variance and the whole distribution. And finally, as what Dr. Sun mentioned, for the solvers with replications, we are able to provide a statistical optimality probability for those 2 models, NDC and EAE. And then to the validation across models, we provide a Kruskal-Wallis test table for those 3 different validation sets, and a stochastic dominance figure, and generalization error table, and optimization error table. And this is the some of the results we have. So we can see that for the deterministic forecasting model, the predicted objective does not agree with a validation objective confidence interval and prediction interval. So in this case, we can see that the model in this case is not describing this problem very well. And for those the other 2 models, we can see that they are so the predicted objective falls in the confidence interval as well as the prediction interval. And for these 2 models are solved by the stochastic decomposition solver, so that we can also provide a level of probability with the tolerance at this much. And also we draw this stochastic dominance figure. So in this case, it's a maximization of the profit problem. So we can see that the empirical additive error model gets the better profit for this case. And in general, we can divide all these steps in 3 phases, and to be able to reproduce this kind of problem, and so we create this core platform. So I will quickly go over that. So we in this platform, we would like to integrate the open source data analysis functions as well as the optimization solvers. And in the meantime, we are able to provide the validation and visualization tools. And note that all these steps in this figure can be easily replaced and reused by other examples, so that you can, maybe you have a new alternative model here, and you can easily reuse the predictive model and the validation models here. All right. So this shows a structure of this platform. So how much time do I have? So I will skip this. And yeah. Yeah. All right. No internet. Oh. All right. Let's see it again. All right. We're here. All right. So this is our platform. You can easily register a new account and create your own instance here. So for each instance, we have a name or short description, different domains, different difficulty levels. Currently, we have 3 difficulty levels. They are pedagogical, advanced, that SSN example is an advanced example, and challenge problems. And we will take a look at this particular example. So, So the contributor can upload a workflow figure here to describe this problem. And we have 3 phases. There are a learning phase. And for the optimization part, we have 2 sub-steps. First one is the modeling. We wrote the input file by using this PySP modeling language. And then we do this stochastic programming step, solve this problem by the stochastic decomposition solver, and finally we have the validation. So let's take a look at the first one. So for each step, you can just easily upload your input file, output file, and link your program. So in this case, we have the advertising dataset sitting here. And then for the learning model, we use the Jupyter notebook here. And then you can see that we read the data from our platform and run a linear regression model. And
This is in R, right?
yeah, this is in R, yeah. And we also provide the variance covariance model because we have that NDC model. All right, so then this is the first step. And for the PySP modeling and stochastic programming modeling, we have another piece of software developed by my colleague Jiajun here, and which is on our website. You can easily download that from GitHub, and it will look like this here. So once you have your PySP model here, you can easily generate a new example. Let's call that advertising train here. And then it will call the PySP and generate the SP input in the current project folder. And then you just click the solve button. It will call our SD solver automatically. And we will solve for 30 replications for this example. All right. And after you are done, we have the SP output files all stored in the project folder. And then we can do the validation here. First, import the datasets. We have this deterministic forecasting and NDC and this empirical distribution. All right. Open those. And we are able to provide this cross-Corvallis test table here, which is also installed here. So our assumption is that those two distributions are significantly different. So in this case, all those three p-values are quite small, so that we can say that the distribution of the... Okay. I mean... yeah, these three values. So the validation data sets for those three different alternative models are significantly different. And we are also able to provide this information graphically so that it will generate the stochastic dominance figure here, which is here, not within run, across run, like this. This is the same figure I have presented in the slides. So that with our platform and this software, all these different steps can be done easily. So this is one of our goals to present this, right?
So what I'd like to see is if any of you are interested in contributing to this effort. And so if you are interested, please put your name down on this sheet of paper. There's many more pages here available. So if you put your name down, we'll send you an email about how you can get into the system. Okay? We don't want to spam you, so if you can put your name, then we'll send it along. You can be either a user, in which case you're only going to be using what is available directly, or you can be a contributor, which means you put up your code as well. Okay? So you can do either one. And please, if you don't mind, just either write your name and email or pass it along. Okay, now we are ready for questions, if it's okay.
One or two questions?
One or two questions. I told this gentleman here that I'd come to his question.
Okay, go for it.
You know my question very well.
No, I don't remember it.
For the optimization and statistical learning, for the optimization, you said that we don't have confidence intervals, right?
No, we don't.
Then I ask
we don't have prediction intervals. We have contributor intervals.
So then and I ask for the mean variance model in financial optimization. We have a